All right, in class we talked about periodic trends, and I know some of these can get pretty complicated and confusing, so we're going to go through these a little slower and make sure that you have something to reference if you need to. So there are 4 periodic trends that you need to know, and in this video we'll talk about 2. We'll talk about atomic radius, so really just looking at how big the atom is, and we'll look at ionic radius. So for both of these, as just a quick reference, you need to know that for atomic radius, going from left to right on the periodic table, it decreases. So the atoms decrease in size, and once we look at it, you'll see that that's a little odd, but I'll explain to you why that happens. And then from top to bottom, it increases in size, and this is much more intuitive, and we'll see why that happens in a minute as well. For ionic radius, from left to right on the periodic table, it also decreases. However, there's kind of a weirdness that happens around group 15. It starts over. And I'll show you exactly why that happens. It has to do with the ions and what atoms are more likely to make what kind of ions. And then from top to bottom, it's the exact same as atomic radius. It increases in size. Okay, so let's look at a couple of examples so that I can explain to you really what's happening. So from left to right, and I recommend that you reference your periodic table while we're talking about this. From left to right, the atomic radius decreases. Now, it doesn't really make sense because we know that from left to right, the number of atoms increase and the number of electrons increase, but the size decreases. So why is that? Well, I'm going to take lithium as an example, and we're going to look at oxygen as an example. So from left to right, this is how they are organized on the periodic table, and they're on the same period, the same row. Okay, now lithium has 3 electrons. Okay, so the first 2 electrons are in its first energy shell, and the third electron is in its final energy shell, its outer energy shell. For oxygen, it has also 2 here, and then it has 1, 2, 3, 4, 5, 6 electrons in its outer shell. So what I want you to notice is that lithium and oxygen both have the same number of shells. So they both have the 2 on the inside shell, and then they have that outside shell, except lithium has fewer electrons than oxygen. However, lithium is bigger, oxygen is smaller. So why is that? When we look at these, something you need to realize is that you can't forget about the protons in the center. So lithium, since it has 3 electrons, it also has 3 protons, those positively charged particles. Oxygen, since it has 8 electrons, it also has 8 protons. So the deal with this is that while oxygen has more protons and more electrons, oxygen's 8 protons have a much tighter grasp or a much better pull on all of these electrons. So it pulls on these electrons much harder than the lithium protons do, because there's only 3 protons there, and they're pulling on these 2 electrons and then that 1. Here you've got your 8 protons, it's pulling on these 2, but then those 8 are also pulling on the 6 out here. So the fact that you have more protons in the middle here has a tighter attraction to all of these electrons out here. So this atom ends up being smaller and just tighter in comparison to the lithium. So that is why from left to right, the atomic radius decreases. It's actually getting smaller because that pull is much stronger. Okay, so it's becoming a much more compact element, atom. Now, from top to bottom, this makes a lot more sense than from left to right. Think about lithium. It only has 2 shells. And if we look at, let's say, potassium, this is the one we looked at in class, it has 4 shells. I won't draw all of the electrons because that's just too much, but it has 4 shells with electrons. Now, it just makes sense that it would be much larger than this lithium simply due to these extra shells of electrons. So as you go from left to right, the atomic radius decreases. As you go from top to bottom, it increases. So this is left to right, top to bottom. Okay, so if you look at the periodic table, lithium is above potassium, and it is increasing in size. Again, this makes much more sense. Potassium has a lot more protons and a lot more electrons than lithium. But that can't be the only reason. It also has additional energy shells, as opposed to oxygen, which has more protons and more electrons, but the same number of energy shells. So those electrons are essentially the same distance, but those protons in the nucleus of the oxygen atom have a stronger pull, so it makes this atom a little smaller. Now, ionic radius is very similar. The same thing is happening essentially. It's just that there's this new thing going on regarding group 15. And let's look at why that is. Okay, first we're going to look at lithium again, and we'll look at boron, and we'll look at fluorine. Okay, and actually let's also look at nitrogen, so that's in group 15. Lithium is going to make an ion, and since we are looking at ionic radius, we have to look at what ions are they going to make. Lithium is going to make a +1 cation, boron is going to make a +3, nitrogen will be -3, and fluorine will be -1. So we have to kind of visualize what is happening with these ions, right? So here's lithium. It normally has these 2 electrons and then this one. And here's boron. It has these 2 electrons, and then in this shell it has 3. Boron's atomic number is 5, therefore it has 5 electrons. But it's going to be much easier, for lithium to lose this electron than it would be for it to gain 7 in order to complete the octet rule. So it's going to lose that electron. So now lithium with a +1 charge looks like this. Now it has 3 protons, so don't forget about the number of protons, that's not going to change. But now it only has 2 electrons. Okay, so 3 protons, 2 electrons. Okay. Boron is also more likely to lose those 3 electrons than gain 5. So boron with a +3 charge is going to look like this. But also it still has 5 protons, and now it has 2 electrons. So realize that as you're going from left to right, your increased number of protons is going to have a stronger pull on those 2 electrons. So from left to right, it's decreasing again. Just like with atomic radius, from left to right it was decreasing. Now once again we're looking from left to right is decreasing again. Okay, well now let's look at nitrogen and fluorine. Nitrogen has its 2 electrons here, and then it has its 5 electrons in the outer shell. Now, when nitrogen makes an ion, it's much more likely to gain 3 electrons rather than lose 5. So it'll actually gain 3 electrons, so then it'll be Na3-. Remember, those electrons are negative, so when you are adding electrons, you are actually creating a more negatively charged atom. So once you have added those electrons, now you end up having oh, not, I'm sorry, not sodium, nitrogen. Now you end up having nitrogen with 2 shells. And remember, nitrogen has 7 protons, but now that it has gained 3 electrons, it has 10 electrons, so it has a -3 charge. Fluorine does the same thing. So we'll start with fluorine. It has 2 electrons here, and it has 1, 2, 3, 4, 5, 6, 7 electrons here. When fluorine makes an ion, it's going to make a -1 charge. So it's going to add an electron right there. So now fluorine is 1-. You can also write -1. That's fine too. So now fluorine is going to have these 2 shells, but we've got fluorine typically has how many protons? It has 9 protons. And now that we added an electron, it has 10 electrons. So notice that you have that increasing number of protons in the nucleus. So as you're going from left to right, that size, that ionic radius is going to decrease for the same reason that the atomic radius decreased, because now those protons in the nucleus have a stronger pull on the electrons. So all of these electrons that are here are going to be pulled closer to the nucleus than the electrons here, simply due to the fact that you have more protons, more positively charged particles here than you do here. Okay, so watch the next video to get periodic trends regarding ionization energy and electronegativity.